You're listening to Worth Electronics' What's Up radio podcast, and each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic tech specialists, and they're going to shine a light on some topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast. As a result of the constantly growing number of applications based on networked communication through data lines, it's becoming increasingly important to ensure trouble-free operation, as well as the safety of those electrical systems and devices. By filtering directly at the interface emissions, electrostatic discharges, or ESD, and fast transient bursts are prevented from entering the system and therefore negatively influencing the operating performance. To verify the EMC properties of electrical systems, special tests are carried out in accredited EMC test labs. Now, if these tests are not passed, the application has to be fully revised. In order to simplify this process, an adapter stick was designed, and it contains a complete filter circuit for the selected application, and it can be plugged into the appropriate interface. The simple plug-in allows a quick check of the filter effect on the system to be tested. And once the tests are passed with the filter stick inserted, the circuit can be implemented into the system. Today's podcast is split into two parts describing the design of the filter stick for the RS-485 transmission standard. Beginning with a basic introduction, we'll then move into the selection of the components, discuss the technical equations to find the right components, and then end with a discussion on the filter circuit of the supply voltage line. Because there are multiple equations included in this podcast, you can find them as figures in most podcast streaming networks, or visit our website at www.we-online.com/appnotes. Let's begin. Now, since no connector is defined for RS-485 applications, 9-pin D subconnectors and the pin assignment defined by Profibus, this ensures the widest possible range of applications. Our pin assignment is as follows. On pin number 3, we have the data line B. Pin 5 is the ground, pin 6 is the supply voltage line, 8 is data line A, and the enclosure is ground. Before the selection of the components for the filter circuit is made, we need to define the required effect. The selected RS-485 interface requires a high level of protection against common mode interference over the entire frequency range. In addition, all signals with frequencies that do not correspond to the transmission standard should also be attenuated. There must also be protection against overvoltages on the data line. The supply voltage line should provide a uniform and interference-free voltage. In this section, the components necessary to achieve the desired filter effects are selected and dimensioned. Typical procedures are calculations by transfer functions and simulations. There are a bunch of helpful online tools, such as Worth Electronics' Red Expert platform, and this helps to compare characteristic data and real measured values of individual components with each other, and thus select the suitable component for your circuit. It's classified into filters for the data line and the supply voltage line, since different requirements are placed on the filters. Let's begin by discussing the filter circuit of the data lines. First, a common mode choke needs to be selected. Here, it's necessary to determine the frequency at which the line could act as an antenna and therefore cause common mode interference. This limit is reached when the line length is equal to a quarter of the wavelength, which we will call lambda. Beyond this length, the line can no longer be considered a lossless short circuit since the parasitic effects reach dimensions that cannot be neglected. Relevant for this calculation is the maximum possible cable length for RS-485 applications, which is specified at 1.2 kilometers. Our equation follows a value of 4.8 kilometers for the wavelength lambda. With this, the cutoff frequency is F sub lambda divided by 4. And this is done for the first assumption of light in vacuum, but it may vary depending on the transmission path used. Using our calculation, our cutoff frequency is 62.5 kilohertz. So since the frequency increases with a decreasing cable length, it is necessary that the common mode choke already has that high attenuation at 62.5 kilohertz, and then it increases for larger frequencies. In our attached figure 1 of this podcast, you can find our calculation for the cutoff frequency, as well as the common mode insertion loss of the component that we used, the WE-SL2. And it can be seen that the component already has a high attenuation of approximately 16.5 decibels at the frequency F sub lambda divided by 4, equaling 62.5 kilohertz. Then we select the Esd Suppressors, and this is for overvoltage protection. An important parameter here is the value of the applied voltage. As the data lines need to be protected in this case, an Esd suppressor with a voltage specification of 5 volts is selected. There are Esd suppressors specially specified for RS-485 applications with the article designation in the Worth Electronic Catalog. Another value relevant for the filter circuit is the capacitance, which is included in the total capacitance of the circuit. The capacitance of this component is 56 picofarad. Now the filter is ready for common mode noise as well as overvoltages, but it still needs sufficient protection against differential mode interferences. The last components used to protect data lines are the capacitors. Since all other components have already been selected, the required total capacitance should lead to the desired attenuation against differential mode interferences, and this can be calculated using a transfer function. In order to set this up, the overall equivalent circuit for differential mode needs to be considered. So this consists of the termination resistors at the beginning and the end of the line, an inductance, and a capacitance. This is where we really get into those equations. From this setup, we can build an equation derived for the transfer function. You can find this equation in figure 2 of this podcast, or you can follow along. Our equation is x sub C1 times R sub 2 divided by x sub C1 plus R sub 2, all divided by R sub 1 plus x sub L1 plus x sub C1 times R sub 2 divided by x sub C1 plus R sub 2. And this equals U sub A over U sub E. Again, you can find this equation in figure 2 of this podcast. But that equation shows us that X sub L is the reactance of the inductor L sub 1, and X sub C is the reactance of the capacitor C sub 1. So according to the standard, the maximum transmission rate of the RS-485 standard is 12 megabytes per second. Since RS-485 transmission uses NRZ, or non-return to zero encoding, the transmission frequency, Fmax, can then be calculated as Fmax equals the maximum transfer rate divided by 2. So this equals 12 megabytes per second divided by 2, which gives us 6 megahertz. Since all signals up to this frequency are to be transmitted unhindered, a desired attenuation of -3 decibels at a cutoff frequency, or 15 megahertz, is specified to ensure a certain buffer. Due to the design of the circuit as a voltage divider, a basic attenuation of -6 decibels must also be included in this value. The total attenuation is calculated to be -9 decibels, which in turn corresponds to a total voltage ratio of around 0.35. In this case, the voltage ratio of approximately 0.35 is the amount of a previously unknown complex number, which, as we mentioned earlier, is our UA over UE, so that now equals Z. Due to the termination of the RS-485 applications, the resistance value for R1 and R2 is 120 ohms each. For the value of the differential mode inductance L, the value for the leakage inductance of the common mode choke, LS, equals 90 nanohenry, and that's used from the data sheet, since the common mode inductance is canceled due to the opposite currents of the signal. The last unknown parameter in the transfer function is the reactance, or our X sub C of the capacitance. This simplifies our previously mentioned equation, so we now have X sub C1 equaling 7 times R sub 2 times the sum of X sub 1 L1 and R sub 1. This is all divided by R sub 2 minus Z times the sum of R sub 1 plus R sub 2 plus X sub L1. Since the reactance of the capacitor does not contain a real part, it can be set to 0. Therefore, the formula must be divided into a real part and an imaginary part. So this new equation can be complexly conjugated so that there is no imaginary part in the denominator, while a complex number remains in the numerator. The real part of this complex number is set to 0 and converted to one of the parameters A or B. The real part of this complex number is set to 0. This means that now 2 equations for 2 unknown variables are available, meaning we can solve our equations. If we have a real part of 0.23, an imaginary part of negative 0.27, and a complex number of 0.23 minus j times 0.27, it results in a total capacitance of 181.38 picofarad. This means that to achieve the desired attenuation of negative 3 decibels at 15 megahertz, the filter structure must contain a total capacitance of 181.38 picofarad. The first contribution to this total capacity is made by the Esd Suppressors with a capacity of 56 picofarad each. Since these are parallel to the circuit and connected to the ground, only half of the capacitance of one component is included. As a result, the 2 Esd suppressors influence the circuit with a total capacitance of 28 picofarad. According to the same principle, 2 capacitors are built into the circuit. These are used to divert high-frequency interference. Combined with a common mode choke, this design offers very high protection against common mode interference over a wide frequency range. A small capacitance is sufficient to achieve the desired effect. 2 capacitors with a capacitance of 100 picofarad are selected, and the effect of the capacitors is calculated as with the Esd suppressors. Therefore, the 2 capacitors act with a total of 50 picofarad on the circuit. In addition to the common mode choke and the 2 capacitors, which are connected to the ground, a capacitor is also inserted between the data lines A and B to counteract the symmetrical interference. Since the capacitance of 78 picofarad is already present in the system because of the Esd suppressors and the 2 other capacitors, a capacitance of 100 picofarad is selected for this capacitor. By selecting the components, a total capacitance of 178 picofarad is now achieved, and this deviates only 3.38 picofarad from the calculated total capacitance. The deviation is unavoidable, and this is because of the fixed capacitance values of the capacitors available in the range of products, and it's been kept as small as possible with this selection. Since the circuit is to be kept small, only MLCCs are used, and the component selection for the filter circuit is now complete. To check if our selected components actually achieved their desired effect, the circuit can be simulated using LT Spice. The VDE standard EN55017 specifies that the differential mode test circuit must be simulated through isolators with a winding ratio of 1:1, since the simulation only considers 2 ports. In addition to the selected filter elements, serial resistors at the beginning and the end of the circuit are inserted to take the influence of the impedance-matched microstrips on the PCB into account. The data lines of the filter stick were designed with a differential impedance of 120 ohms, which equals 60 ohms per microstrip, to avoid reflections at the ends of the RS-485 bus, which are terminated with 120 ohms. In our attached figure 3, we see the simulation result for load by differential mode currents as they exist in normal operation. The attenuation of the entire circuit is displayed, with the y-axis showing the level of attenuation in decibels and the x-axis showing the corresponding frequency range from 10 kHz to 1 GHz. Measurement takes place at the output of the circuit. The -6 decibel basic attenuation is due to the simulated circuit being designed as a voltage divider. We see here that the signal is not damped in the transmission range of the RS-485 standards, which is less than 6 MHz. The marker point is at approximately 15 MHz and shows an attenuation of around -9.18 decibels. This shows that the design, with the help of Red Expert and the calculation by the transfer function, leads almost exactly to the desired result. The deviation of -0.18 decibels can be explained by the small difference of the used and the calculated total capacitance, and the fact that models of real components are used for the simulation, while ideal values were assumed for our calculation. For the simulation of common mode loads, the VDE standard EN55017 states that the filter circuit must be inserted between the signal generator and the receiver, and that the input and output conductors must be connected in parallel. Because of the use of a parallel circuit, a series resistance of 30 ohms was also added into the circuit to simulate the 60 ohms per microstrip. Next, we'll discuss the filter circuit of the supply voltage line. According to the RS-485 transmission standard, a pure DC voltage of 5 volts with a current of 200 milliamps should be applied to the supply voltage line. To obtain such a clean DC voltage, all frequency components must be filtered out. That means a low-pass filter is required. Due to the characteristic that the attenuation increases per frequency decade with each pole of the filter, a third-order low-pass is selected for the filter circuit. The attenuation is therefore 60 decibels per frequency decade. A low-pass consists of 2 capacitors and an inductor. As a result of its design, it is often referred to as a pi filter. In order to select suitable components that meet the requirements of the filter, the online tool Red Expert is used. The first step is to select the right inductance. It should be noted here that a current of 200 milliamps flows on the supply voltage line. This is important because an inductor designed for low currents would be strongly heated. To prevent this, a PCB ferrite with a rated current of 500 milliamps is now selected. So this means that the ferrite heats up only to about 40 K at a current of 500 milliamps. In addition, the inductance should counteract currents and voltages with frequency components with a certain impedance. We also want to mention that Red Expert makes it possible to display impedance curves at different currents, and the 200 milliamps was selected based on the application. The capacitors for our pi filter are selected so that the attenuation range is large and as steep as possible, and that all currents and voltages with frequency components are well conducted to ground. For size reasons, MLCCs are used for the data lines. The article We CSGP has a capacitance of 1 nanofarad, and we selected that. So the capacitors selected are made of X5R ceramic. This enables a high capacitance. However, due to its internal structure, the material is also very voltage dependent. An applied voltage leads to a drop in capacity, and this effect is called DC bias. How exactly this effect affects the selected capacitors can be seen in Red Expert. In our test, the capacitors at 5 volts affect the circuit with about 42% of their original capacity. Because of the current dependence on the ferrite and the voltage dependence of the capacitors, it's important to test the circuit under the conditions of the application. First, the effect of the selected pi filter is simulated in LT Spice, and Worth Electronic components are available as models in LT Spice. This allows simulation to be as accurate as possible. An AC voltage source with an amplitude of 1 volt is used. Due to the construction of the simulated circuit as voltage divider, there is again a basic attenuation of -6 decibels. As expected, our markers show that the attenuation per frequency decade is 60 decibels. We also see that the entire frequency range shows good attenuation. However, the high maximum attenuation value of approximately -158 decibels is conspicuous. Now, it's questionable whether such a high attenuation can be achieved with real components. Also, the most network analyzers reach their limit at -100 decibels. Now all required filter elements are selected. Since the simulations show good results, the circuit designs are built with the selected components. However, the simulations do not relate to all the factors present in circuits, such as material influences and line losses. Therefore, measurements are required to show whether the structure actually meets the requirements for high safety against interference signals and transients under real conditions. This concludes part 1 of our podcast series, Adapter PCB for Filtering Electromagnetic Interference on an RS-485 Interface. In our next episode, we will continue our discussion beginning with PCB design, measurement of the S parameters, and then wrapping up with our evaluation and conclusion. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. To download the complete application note we discussed today, visit Worth Electronic online at www.we-online.com/appnotes. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're checking in with leading industry experts and Worth Electronic technical specialists who will shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.